Maybe?
Yeah.
All right, so great. So I'd like to introduce Greg Henselman. Will be speaking to us on Matroids and canonical forms, theory and applications. I think the original title, and here's the updated one.
Right.
All right, thanks a lot, Greg.
All right, thank you so much, Peter, for inviting me. A lot of reasons for this talk, but sort of the main one is directly addressed by the title. This is something that I've encountered in working with persistent homology and working with other people who are interested in working with persistent homology and applications. One of the biggest challenges that we really often face is explaining what the mathematical objects that we're working with are and what they mean to people who aren't mathematicians, aren't topologists, and for whom the classification theorem for gradables over a PID doesn't mean that much. And it turns out, okay, you can explain these things in a completely rigorous way without going through the algebra. And in fact, you drop the algebra, which it turns out to be really a distraction from a lot of the core mathematical structure that we end up caring about. And a lot of things is clear, and that's not just for people outside the field, it's for people who are pretty devoted and regular applied topologists. Just jump into this. There's very little combinatorics that we're going to need. Basically, just some definitions, and these definitions are things that everybody is pretty familiar with, who's taken an advanced course in linear algebra. So I say that this is going to be a story that's a continuation of a long program started by Whitney in 1935. And we essentially to take one combinatorial property of independent sets in a vector space, linear independent subsets of a vector space. Let's say subsets of a basis. Take one combinatorial property of those family of sets and see if you can prove in general without appealing to any of the algebraic structure that vector spaces have. And as it turns out, you can prove a great deal, and if you had a good linear algebra textbook, you might already have things proved this way using something called the Steinitz exchange lemma. Let me tell you what the Steinitz exchange property means. It's a very intuitive property for vector spaces. It's that any time I have two linearly independent subsets of the same vector space, say in this example, I have a set of two blue points and a set of one red point. When you have a strictly larger independent set, you can always find something from the larger independent set to add to the smaller one and get an independent set out. You can always do this because a larger independent set will spin a subspace of greater dimension. And you can always pick something out of that subspace of greater dimension to add to a subspace of smaller dimension. This example, I have these two blue points. They span a two-dimensional subspace. I have a red point. It spans a one-dimensional subspace. So I find a blue point to add to my red point and get a two linearly independent subset of three space. So that's the exchange axiom. Exchange lemma says that independent subsets of vector spaces satisfy this axiom. You can have bigger independent sets of the smaller ones. Okay. Was to take the exchange axiom as an axiom, family of subsets of a set E. We'll add one more requirement that family of subsets be closed under inclusion. So it gets a simplicial complex. social complex with this exchange property. If you're curious, yes, these things as topological spaces have all sorts of nice properties. They're shellable. Homology is all kind of clustered in the top dimension. That's been studied a lot. That's not what we'll think about today, although it's very nice. That this long-running program of Whitney has had far-reaching implications in a lot of different fields of mathematics. A basic role in algebraic geometry. It plays a basic role in mechanism design, optimization, branches of just geometry, graph theory. Some of our best and earliest polynomial time algorithms in theory come from Matroids, as well as a lot of from computer science, because these objects are in some sense so simple, really hard for them not to be relevant in a lot of different situations. And as it turns out, things I care about structurally tend to be structures that are entirely determined by a matroid that underlies whatever object that we're working with. So we're going to need just a couple more definitions involving matroids, and here I hope that everybody will take peace admin and hop in, because this presentation was really designed to be a little bit interactive. I'd love to get some responses from the audience, a couple questions. So here are the only definitions that we need. The restriction of a matroid. Remember, a matroid is a set E together with this collection of subsets that satisfies this exchange property. The restriction of a matroid to set S is just the matroid you get when you take that subset S as your ground set, and independent sets you take all the things contained in S. So that's in matroid. So in the picture, the definition, you see there's a mixture of 3 space, and then there's a wedge in 3 space that looks like the disk intersect quadrant in the plane. Excuse me for just one moment. So, is this wedge in the plane? And a question is, what are the independent subsets in this wedge? Would anybody care to venture in an answer?
So, Greg, what are the independent sets of the bigger space?
I'm going to say the independent sets in the bigger space are the linearly independent subsets of 3 space. So the totally normal, in the abstract, independence means the same thing as linear independence for the original matroid.
So the restriction of that being linearly independent sets in the thing?
Yeah, they're the sets of non-collinear points that lie in that wedge. That's all. That's all. So now a convenient property, because it's true that when you do this restriction operation, the independent subsets contained in that wedge still satisfy the exchange property. The restriction to S is still a matroid, and means in particular that maximal with respect to inclusion independent subset is a maximal with respect to cardinality subset. And find the rank of S to be the rank of a maximum cardinality independent subset. So the rank of the original matroid 3 space would be 3, and the rank of the wedge would be 2, because that's the size of the biggest independent subset you can have in the wedge. One more definition. So then is contraction, and contraction is a lot like a quotient on a vector space. So see the definition of contraction written on the screen. Let's tell you what contraction means if the matroid that you start out with is a vector space, say 3 space. That picture on the right is a picture of 3 space, and the set that you're contracting by is the mid contraction is essentially what you get if you take the normal quotient construction for vector spaces, collapsing all your vectors into a coset. Just leave all those vectors kind of ungrouped by equivalence class, but you treat them as though they are elements of coset, and then you ask whether they're would from an independent subset of the quotient space. Let me give you a couple. So the space on the left here is the original matroid you're starting with is 3, and then we have this one-dimensional line, S, that's our going to contract. So you can see on the left, I've highlighted 3 different points. And let me ask, do you think that those 3 points would be independent in the contraction of the original matroid by that line?
So is the answer.
Yeah, absolutely not. And why not?
You just point lines to make them dependently dependent.
Absolutely. And if you like, you could even say, okay, suppose that those 3 points were independent in the contraction. That would mean that you had to be able to add those 3 points to some point, dependent point on the line and get an independent set. That would mean that the original matroid had rank 4. Definitely not the case. In the center screen, again, we have a matroid, 3 space. We have a subset, the wedge. Those highlighted points, would they be independent in the contraction of 3 space by that wedge?
Too high of a rank, you'd have rank 4D inside this 3 space.
Absolutely, that's exactly right. And moreover, that one point, the point that lies on the XY plane, actually lies in the span, the linear span of those points on the wedge. So there's no way that you can add that point or have that point be independent in the contraction by that wedge. I think that was Henry. Is that right? Thank you, Henry. Let me, thank you, whoever it was.
No, me.
Great. Great. So just one more example quickly. These 2 points on the left, would they be independent in the contraction of 3 space by that line?
Again.
Yeah, not. Because again, you can't add those 2 points to a linear, like a point on that line, and still have an independent set. Otherwise, in the center screen, that one point isn't going to be an independent set in and of itself, because you can't add it to a basis for the wedge and still have a linearly independent set of 3 points in the XY plane. Okay. So, not to belabor this point, the purpose of this exercise is just to emphasize, the level of the definitions that we're working with. They are really involved, and if you sit down with them for 10 minutes or so, you can get pretty comfortable with them. Last definition that we have is to say that a basis generates a family of sets. The intersection of that basis with each set in that family is a set. So again, these 3 points on the left, that's a basis for a 3 space. Would it also generate the one element family of sets that is the line? So do those 3 points generate the line?
So none of those points in the line. So when you take B intersect S, then that's going to be right.
Right, exactly. So there's no way that they could possibly generate the line. Without the wedge in the center of the screen, do those 3 points generate the wedge?
Is this in the wedge, but not 2?
Right, a little ambiguity. It's possible one of those points might lie on the wedge, but if it did, that set wouldn't generate the wedge because the intersection with the wedge has to be a basis for the wedge. Question, do those 3 points generate the XY plane?
Yeah, 2 points, 2 linearly independent points.
Exactly, yes, that's exactly right. Okay, so those are the definitions that we need. We need restrict, we need contraction, and we need to know what it means to generate a family of sets. Okay, ready to go. Let me skip over some of these examples. What I promised, or what I indicated, was that there was going to be some roadmap for connect the dots between persistent homology and things that engineers, scientists, people who maybe aren't pure mathematicians would be able to grasp rigorously and work with on a research level. Let me try to relate or explain him about to say in the language of something that most people are familiar with, which is German bases. At least the engineers and scientists are familiar with this language. Everybody that a filtration of vector spaces is a nested sequence of vector spaces that terminates with the whole space, whatever the whole space is or means. And let me give a second definition of a filtration or characterization. We filter filtration as a function with linear sublevels into the non-negative integers. And we can associate the sublevel sets of that function with a filtration. So I'm going to create a filtration as both a sequence of subsets and an integer valued function. This, I can about the sequence spaces I get thought of as a sequence of matroids, and I'm going to say a filtration by a basis if and only if minimum weight with respect to that basis. So by minimum weight, let me what I mean by that. If you have a function on a vector space, you really get a function on finite subsets of that vector space. Given the value of your function on all of the elements, and does that make sense? Great, thank you. Okay, so let me very briefly try to explain to you why there should be a relationship between minimum weight with respect to this function of generating a filtration. So start with any filtration. Say the one on the bottom generates my filtration F. These rectangles that you're looking at are kind of my Venn diagram of nested subspaces. So we think of filtration as left to right, including lighter and lighter subspaces. So the first subspace is represented by this dark gray block, and this level of the filtration is the dark gray block plus the lighter gray one, etc., etc. These white points at the bottom, they represent a basis in my Venn diagram representation vector space, and they generate the filtration that's indicated by these shadings. And up above, it's just an arbitrary basis. I don't know if it generates my filtration or not. Well, let me an arbitrary basis. And we prove to you that if it doesn't generate F, then they say that it could possibly have minimal weight with respect to F.
So sorry, can I interrupt?
Yeah.
Okay, so I'm confused here. Can you explain the top of this picture, or the top half of what the arbitrary basis is? So the white dots are elements in your basis.
That's right.
And going left to right, these are basis elements that are kind of extending the filtration. We're seeing through the filtration.
So we have a filtration of vector spaces, and kind of each shaded blocks represents kind of the next level in the filtration as you move left to right.
So 0, two-dimensional vector space.
That's right. Yes.
And F1 is a three-dimensional vector space.
So F1 is a four-dimensional vector space. So the basis on the bottom, we're going to say, is the one that generates the filtration.
Okay.
Top is just
up the bottom. Okay, there. So F is there. So F0, 1, 2, and 3, which have 2, 4, 6, and 8.
That's right.
And represents basis elements that are compatible with that filter.
Yep.
Okay.
Yep.
Okay. So basis, you mean a basis is some other filtration of that vector space. Is that right?
It's just any basis. I pick any basis for the vector space. I might not have a special relationship with the filtration, but I just choose a basis.
Okay.
Right. And I say, if that basis doesn't generate the filtration, then there's no way they have minimal weight with respect to F. I think here.
So I guess I didn't. Well, maybe I should be able to figure it out. Again, what minimum weight means then?
Right. So if I have a function, just a valued function on the vectors of a vector space, I can actually get a function on 5 subsets of vectors, assigning the sum of the weights of the elements in a subset to that subset. So a set of 3 vectors and each one had a value of 1, then the weight of that set would be 3.
Okay, so in the bottom picture, since that basis equivalently, so like the first 2 white dots have 0, so they give weight 0 plus 0 equals 0, and then the next 2 give weight 1 plus 1 equals 2, and then 2 plus 2 equals 4, and 3 plus 2 equals 6. Weight.
Yep.
Okay, thanks.
Yep, exactly. So how would we show this? How would we show that you generate the filtration to be minimal? Well, let's take that arbitrary basis, and let's just suppose that it doesn't happen to generate F. Well, it means we can look at some filtration level. We can look at the lowest possible cutoff, where this arbitrary basis doesn't contain for some filtration level. So in this picture, the base on top doesn't contain a basis for kind of the first 2 levels of the filtration, or the second level of the filtration, because that level is dimension 4, and our arbitrary basis only has 3 vectors in that space. If that's the case, well, we can take the basis that generates this filtration, and we can move one of those vectors up into the arbitrary basis. Now that results isn't if it has too many vectors, but we can construct a basis with these 4 points, the basis that we've just generated for kind of filtration level 2, and those 4 points which are independent, we can start adding others from that arbitrary basis and build ourselves back up to a basis. That new basis will consist of basically the arbitrary basis that we started with, minus this black point plus this white one. And you always do this Of course, once we've made that exchange, once we've taken the black point out and added the white one in, we strictly lowered the weight of this arbitrary basis because we've taken out a vector that takes a higher value on and put in something that it takes a lower value on. That's how you prove that every minimum weight basis generates the filtration, and it's easy to see that every basis that generates the filtration has to have minimum weight because everything that generates the filtration has the same weight. So, of sophistication, you need to prove results with Matroids, at least on the level that what's going on with homology and percent homology. It's very ground level stuff, and it's stuff that you probably wouldn't want to communicate to a scientist if you were sitting down with them, but it's something that you could very easily translate into their language if you needed to make a point to them about something that was going on. Okay. All the tools that we need to try to cast something about think about in topology and persistence in terms of Jordan bases. So let me tell you the main observation about Jordan bases. And it's interesting. If anybody knows of something similar to this, I'd be interested to hear about it. I've looked for a while. I haven't found anything about the relationship between Matroids and Jordan bases, which is surprising because this is the only characterization of a Jordan basis I've found apart from the definition. I've looked at a lot of linear algebra textbooks. I've looked at a few algebra texts. Interesting, I don't know of a single characterization of a Jordan basis that doesn't just use this definition of Jordan basis as a collection of orbits. I think that's unfortunate because once you realize that Jordan bases are really Matroid theoretic objects, you understand them a lot better. You can classify them and you can understand their structure. Ends up being what we do in topology. So here's a proposition at the top of the screen. The Jordan bases of a nilpotent operator are the orbits of k-minimal bases in V mod T. And what I mean by that is the Matroid quotient, the linear space quotient, and Matroid quotient because technically contraction is not a quotient operation in any of several categories of Matroids. It's kind of its own beast, which is related to quotient operations, but interesting for a number of other reasons. Yes, the bases of a nilpotent operator are, and when I say the orbit of a set, if a collection of vectors, the individual vector under a nilpotent map is the collection of all vectors you can express as t times that vector, t to some power times that vector, until 0. So let me give an example. A collection of vectors u, v, w. If say t cubed u is 0, the orbit of u is going to be u, t squared u. If to the fourth times v is 0, then the orbit of v has length 4. And this function k, so the k is both a filtration and a function, and what that function do, it assigns to each vector the length of that vector's orbit. All right. Is that okay? Okay, great. So let me prove this proposition. It's beautifully simple, easy how you do this combinatorially. And once you do it, you'll never want to prove the existence of Jordan bases any other way. Let me just do one half of it, the fun half. It's not hard. In fact, it's probably longer to not say it than it takes to say it, but not say it. I'm just prove the part proposition that says if a k-minimal basis quotient matroid. So again, a function on V, and that function gives me a function on all the contraction minors of V, and I find a minimal basis in that contraction minor. The minimal bases in those things that are exactly the Jordan bases of the operator, and there are no others. It's the weaker statement that orbits of those things are linearly independent, that their basis is not particularly hard. So how would you show that that of one of these minimal bases is independent? Well, suppose that I start with the basis.
So, why k of W5 and not 2?
That is a typo. So k of W should be 2. Thank you.
Okay.
Yeah. Get that off the screen. So let me suppose that this U, V, and W left hand of the screen, that bar is there is a dividing line kind of for visual clarity. So let me suppose that U, V, and W form a basis for this quotient matroid. And to the right of the line, I've just drawn a pictorial representation of the orbit of this set. Okay, so this set is the union of the orbits of the elements. Suppose for a contradiction that orbit, that set of, 9 points on the right is linearly dependent. In case, then I can find some subset of vectors that's linearly dependent. Say there's a dependence relation between these guys, and let me know that it's minimum-dependent, so in particular, I can't drop one of these guys without a dependent set. So that's the minimum number of things in this triangle you need to form a dependence relation. Okay, you can factor as many powers of t possible out of the equation to get 0. And what factorization means is really that if I take kind of corresponding linear combination of U, V, and TV, sorry, that TW ought to be a TV. Apologies. T times that linear combination of 3 vectors is 0. Okay. Well, let's be the linear combination of things inside the parentheses. So again, it's a linear combination of things inside the triangle. And it would happen if I tried to replace U with X as a basis vector for my quotient. All right. This is TW, it should be TV. Adding TV to my vector U isn't going to change whether or not the coset of U or basis with the other coset in my 3-element set. I can add anything from a quotient space to something, and I won't really change that coset's linear independence properties. And likewise, I can add V to U, and that won't really change things either, at least as far as the basis is concerned, because I can always add one basis vector to another basis vector and still have a basis. It's an elementary of vector spaces. So is that I can replace U with X in this. And with X, remember, kind of by construction, when I hit X with U squared, I get 0. So I get something with a strictly shorter orbit. And one is that I found of this for my traction matroid that has strictly lower weight than the one I started with. So the whole course of reasoning is that if there's some kind of linear dependence relationship in this orbit of the set, then I can find a basis of strictly lower weight. So you turn that around and take the contraptive, and this says the of every minimum weight basis is independent. As I say, it's fairly easy to then show that that orbit also has to be a basis. Okay, how painful that for everybody else, but I love this argument. I found this argument in a different form in a blog post by Terry Tao, where he essentially said that he never felt like he got a great understanding of Jordan bases, because the approach you see in linear algebra textbooks tends to be very concrete, and the approach that you see in advanced texts using classification of finitely generated modules over a PID can be very abstract. I recommend this post if you want to look it up. This proof essentially a gradient descent method, a discrete gradient descent method, to find one of these minimal bases. He doesn't say it's a minimal basis, and he doesn't really talk about the matroid structure, but hiding in his argument. And I think the important point to be made is in that you do try to approach Jordan bases from this algebraic standpoint, either from kind of the strictly constructive perspective of linear algebra texts, or from kind of the more abstract classification theorem approach. You're being confused by this algebraic structure, and in fact I argue that it's almost impossible to understand Jordan bases if you out things purely in terms of algebraic structure, because these bases, these things that generate units in a Jordan bases, be characterized by linear things. What we need is this weight function, this k, and this k is not invariant on the subspace that you're quotienting by, which actually means that you can't really think of independence as you want to think about it, as independence in a quotient space, and also have the weight function that you need to describe what's going on. A natural place where the combinatorial structure of matroids is the language that you want to use to understand a very basic phenomenon that's pretty broadly relevant in not just applied topology, but in lots of branches of math. So any questions before I move on? Great. I won't try to say a proof for this at you, because it would be easier for me to say it than it would for you to prove it yourself. But this classification, once you understand what basis is in this matroid theoretic terminology, it becomes very easy to persuade yourself, or to prove rigorously, that if you graded nilpotent operator on a graded vector space, that graded Jordan bases exist. You just that you can always find a minimum weight basis that's subordinate to your grading. And that theorem, that result, every graded nilpotent operator has a graded Jordan basis, that is the classification of finely generated modules join T over the polynomial ring K and join T. That's the classification result that we use to define persistence diagrams. And you can prove it from the ground up, from absolutely nothing, a scientist or an engineer or a mathematician, just the combinatorial argument that we just saw, us explaining the definition of a graded map is, which is in general much easier than explaining what a graded module is and explaining even what the classification theorem says, let alone how to prove it. Okay. So let's relate this to persistent homology and how this perspective might actually help us understand something about persistent homology. We already know the definition, and the definition works fine. So that we said that a basis generates a collection of sets, the intersection of that basis with any family set or in that family of sets, basis. So, for example, here on the left and the right, you see the same basis, the same 3 points. And on the left, you see a filtration. It starts with a line in the xy plane, then it goes to a that affects the z-axis, and then all of 3 space. The 3 points generate that filtration. They also generate the filtration on the right. Is that okay?
Yes.
Great. So have this special property. So it come up with examples of sets or families of sets that can't possibly be generated by a single basis. A good example of that is 3 lines, 3 distinct lines in the plane. There's no basis that generates 3 distinct lines, in particular because that basis would have to contain one element from each of those points, and that couldn't possibly be linearly independent. So in general, you can't ask a family of sets to be generated by a single basis, but are sort of so nice, you can ask them to be simultaneously generated. I can give you any 2 filtrations and always find a basis that generates them both. And the proof of that fact is pretty important to applied topologists. So let me go over it. The 3 filtrations is easily shown to be impossible. In fact, that example with 3 lines in the plane shows you can't in general generate 3 filtrations. There's something very special about 2, and this is in fact pretty much right heart of the reason multi-parameter persistence. Not that we can always do. Because if you had to have multi-parameter persistence, you would have to have a basis that generates 4 iterations, which is in general impossible. But let me just go over very briefly the reason why filtrations are so nice, at least when you have 2 of them, that you can always generate 2 with single bases. Let me start by proving that you can always generate 1 filtration with a single basis. That might seem pretty obvious, but it'll set us up for the hard case. So argument. Say I start with the filtration. The filtration here consists of the x-axis, the xy plane, and all of 3 space. Those are my 3 levels to the filtration. I know every vector space has a basis. I'll take that as a given. So say I start with some basis. Now, if that basis doesn't generate my filtration, then I can always find a basis vector, say in the very top level of the filtration. That vector will determine a direction along which I can project. So let me take that direction and project everybody else except for the one that I selected at first onto the level of the filtration. I can essentially reduce the dimension of my problem by because basis vector for this level, and if I can get a basis that generates the filter restricted to the xy plane, then I'll do that. I can iterate the same process. So my 2 points in the xy plane don't generate my filtration in the xy plane. So let something highest filtration level in that plane, that'll give direction along which to project, and I'll use that to project the other basis vector onto the next lower level. And what I get a basis that generates the filtration. And okay, to a pair of filtrations. That every filtration is generated by some basis. Let me choose another filtration, and let's a basis that generates that filtration. So here I have kind of this white line. That's the first of 3 levels, and I have this kind of skewed broad disk, that's my second level, and then again, all of 3 space is third level. And these 3 white points get the filtration. Let me start this as the starting data. I'm going to apply exactly the same algorithm from before to get a basis that generates the white filtration. If I apply exactly the process that I just described in this example, what I get is, again, a basis that generates both filtrations. Now, why am I allowed to do that? Well, at each step, the direction along which I'm projecting that doesn't change, if you look at the right, it doesn't change the filtration level of any basis vectors for the blue filtration on the right. And the
Sorry, Greg, I think I'm confused here. So you've got the 2 filtrations, and then starting off with 3, like an arbitrary basis of R3 is what you're starting with?
So I'm starting out with a basis that generates the blue filtration. That's my starting data for this for one.
I see, okay. And then okay, and go ahead from there.
Start out with a basis that generates the blue filtration, and then I modify it to a basis that generates the white filtration. And I claim that I can perform this modification in a way that preserves the fact that my basis generated the blue filtration. And the way that is very simple. Something you can observe about this blue filtration, if any vector in the space on the right, say it lives on that blue pancake, but it lives off the white axis, the first level of the filtration. If I slide any point on the pancake in the direction determined by that white line through the origin, I'll never move that point on the pancake either onto the white line or up into 3 space off the pancake. And the reason is, if I take any vector on one level of a filtration and I add a vector from a lower level of the filtration, I don't change the filtration level. Essentially moving my vector parallel to some lower filtration. For this algorithm, for getting a basis that generates both filtrations, that when I perform these projections on the left to whittle me down to a basis that generates the white filtration, I can always choose projection directions kind of from the lowest possible blue filtration level, which essentially means I'm always sliding vectors on the direction parallel to whatever filtration level that they're in. This process, this visual process, it's called a UD composition. But people think about it in this geometric way. And even though this explanation maybe does a lot of sense, or doesn't make a whole lot of sense at first pass, I'm really sure that if anybody sat down with these pictures, they could very quickly prove themselves that, yeah, this makes sense. They could prove themselves, they can understand this algorithm inside and out. If you sit down with this for 15 or 20 minutes, you can really get a very thorough understanding. And let me read why having a thorough understanding of this algorithm would be useful. I'm going to apply topologist. Suppose that I have 2 filtrations, a white filtration and a blue filtration. Suppose that the blue filtration consists of spaces that are each contained in the white one, as picture. In this case, I can naturally get a sequence of quotient spaces. Each quotient space is the white filtration level modulo the blue filtration level. So if you look at this column that's third from the right, the white filtration level there is all of 3 space. The blue filtration level is just the x-axis. So quotient is kind of canonically isomorphic to the YZ plane. You can get these quotients, and as we all know as topologists, there are natural maps between these quotients by inclusion on the white space. So we just track where one of these points would go at the bottom. So I start out with a point on the x-axis, natural map that carries its point on the axis in the next bit over, continues on until we get to the third column from the left. Point now lies on the x-axis, and that's in the blue filtration level. When we quote that out, we go 0. And white point hits the origin at the bottom, and then stay at the origin ever after. Take a basis that generates both the filtration and the blue filtration. Opens to these basis vectors, or what they look like under the quotient map. So in the top, what you're seeing is just the intersection of that basis with each of the filtration levels. White, if it's in the white filtration level, and blue, if it's also in the blue filtration level. It's straightforward to convince yourself that in this picture, the white points correspond exactly to a basis in these quotient spaces at the bottom. Being a basis for these quotient spaces at the bottom, the collection of all these bases forms a basis. For the map you get on the direct sum of that bottom row, inclusion that direct sum. Okay, great. So as this picture suggests, Jordan basis is exactly a barcode decomposition. If, for example, your white filtration comes from the filtration of cycles, nested sequence of topological spaces, and your filtration is the filtration of batteries by the same sequence. But what this says is that you can understand persistent homology, you can understand the barcode simply in terms of a basis that generates two filtrations. That persistent homology really is a basis that generates two filtrations. And that's something that a scientist or an engineer or somebody who's not a specialist in our field can understand. In fact, they can understand it fairly quickly. You sit down with them, and in an hour or so, just drawing pictures, they can pretty quickly get a fully rigorous understanding of what these objects are. That require classification theorems. It doesn't require them to know what modules are. It requires them to know what vector spaces are. And do it all in terms that are very familiar to them. I think I've essentially run out of time. Let me just flash some pictures at you to mention, as we said, multi-parameter systems. You can understand why we have some of the challenges that we do in that regime now. And because if system homology is a basis that generates two filtrations, if that's what it really is, if you want multi-parameter persistence, you need a basis that generates filtrations or more. And as we've seen, you can always do that. So sort of a poor proof, if you will, that you can't do what you might like to do in higher dimensions, although it also gives you a lot of information about where you can, stick over the line if you wanted to do something like this, because you know that nature, is pathological, and maybe you can try something that gets at this in some non-pathological cases. And I'll just say very briefly, again, once you understand what these objects are, you can get a much better understanding of what representatives mean. If looking at representatives of homology classes, understand that essentially just in terms of some intersections of sets, intersections of bases for filtration levels in your base of cycles. And yada, something about computation, something about efficient LU decomposition. Basically, you can use something called fundamental circuits, which are Matroid euretic objects, to sparsity in some computations relating to persistence. and really running through things. Mentioned that there is a software package, Irene, out, uses some of the technology used by Matroids and some of the understanding of these bases, and ready to check it out. I'll just mention very, very briefly, there's one thing that I've learned in the short time that I've worked in computation, is that benchmarks are constantly changing. So to take everything in this table with a grain of salt, the main tables you see here are drawn from Paperina Otter and some others who did a great service to the community by doing some benchmarks. The kind of extra rows you see at the bottom are some bench for Irene. And I just want to point out very briefly that if you look at the second column of the second table and the last column of the third table, what you tend to see is that the Matroid theoretic perspective tends to help you in really high-dimensional cases. Because in these very high-dimensional cases, other things break down, but combinatorics doesn't really. And you can apply a lot of the same reasoning from Matroid theoretic concepts to give you a pretty good handle on what's going on in those computations. So I've pretty much run over time, and unfortunately I wasn't able to get to as much as I would have liked to say. Let me just briefly recap the points. Point one, understand Jordan bases. You just understand some very basic facts about Matroids. And if you understand some very basic facts about Matroids, you can actually understand a lot more about persistent homology, and you can communicate more about persistent homology with people who aren't in the field. And what I kind of was conscientiously avoiding saying in this talk, in fact, everything that we do essentially in applied topology can be asked in this language because there's a functor from the category of topological spaces to the category of Matroids with certain maps. And this functor preserves a lot of the information that we care about. And he has really thought about this. There's a huge, wide open field for interaction, and it's very, very easy to get into. So I really encourage anybody, if you have some problem in computation or interpreting your results, understanding what representatives, for example, mean in persistent homology. Don't be afraid to jump into Matroids. They have this scary name. Aside from the name, they're really extremely friendly objects and do a lot of good. So I think let me just close that and say thank you so much for being here, and thank you again to Peter for organizing.
All right. So I guess we don't really have a time limit, but maybe some people have to leave. But don't have to leave. Are there any questions for Greg?
Just a question. So you explained how you can fit compatible bases for 2 filtrations, and you mentioned that you can't do it for 4. Is it the case that you can't do it for 3 filtrations? Yes.
So, for example, if you take that example, 3 distinct lines in the plane, take the filtration. If each of those gives you a filtration that goes line plane, 3 filtrations. And you find a basis that generates all 3 of those, because you would have to have 3 linearly independent points in the plane.
Thanks.
But that's not to say that in nature it might not happen that very often can find filtrations or filtrator generated by a single basis. And it would be interesting to look at from the point of view of multi-parameter persistence.
you. I don't know if other people can.
Oh, sorry. Thank you. Thank you, Henry.
But actually, if I can steal one, well, perhaps I shouldn't do this. So I'll just mention this is an unrelated note. Website. Go to the link for Irene. There's an example of a persistent homology class there. I want to pull up right now for fear of technical difficulties. You can look at this homology class. There's a 3D representation. You can rotate it around, and it's a homology class kind of embedded on the globe. And it traces a line that goes around a big Asia. I read this at a conference recently, and if anybody can explain to me what this persistent homology class is and what it means, I'm very grateful. I have some intuition for how parts of it were formed. Pavel Blotko had some good ideas. But if you go to the website, that will also show you kind of this is a basic visualization capability of Irene. And is something that interests me a lot and relates to these topics of interpreting things and interpreting things combinatorially.
Cool. So I wanted to ask you if you could say a little bit more about kind of the computational aspect. So you gave the idea that we want to find a compatible this compatible with the filtrations of both the cycles and boundaries, and then we can read off the persistent homology from that. Now, there's going to be like vector spaces of like the cycles and simplicial boundaries. So somehow avoiding all the linear algebra allows you to do things faster.
Yeah, so let me say something about that just very, very briefly. Right. Actually, the persistence algorithm boils down to finding these bases, or the single basis that generates two filtrations. Finding a basis of column vectors for some matrix. In essence, you can find that basis in multiple different ways. You can do it by, for example, Gaussian elimination, by performing row operations. You can do it by column operations. You can do it by LU. But those processes kind of, what happens in each of them is kind of equivalent. There's a natural way to go between one and the other. So if we focus just on row operations, for example, I want to find a base of column vectors for a boundary matrix just by row operations. Well, at the end of this process, I'm going to get kind of a matrix that looks like the thing on the right. I have an identity matrix somewhere, and then that corresponds to my basis that I created by row operations, and then I'll have a bunch of stuff in the other columns. To keep track of that stuff throughout the elimination process, you wouldn't be able to find a full basis. What Matroids do for you in this situation is it explains what the structure is of all that stuff on the right in a very simple way. So just very briefly, if this boundary operator that I've reduced is the one-dimensional boundary operator, so the ones correspond to edges, say edges in this annulus that you see on the left, a base for that dimensional boundary operator corresponds to a spanning tree in that graph. Spanning trees are the same as bases for the one-dimensional boundary operator. So just thinking about this basis as a spanning tree help you. Every spanning tree gives you a family of functional circuits. So a functional circuit is what you get when you add one thing not in the spanning tree to a spanning tree. You get this unique cycle in the graph. As that cycle, that collection of edges, responds exactly to the non-zero entries in your matrix corresponding to the edge that you just added in. in the story, I add an edge and it makes a cycle. The matrix version of this story is I have a basis of column vectors, the rainbow on the left. If I add one more column vector, I get a dependent set, which express that thing on the right near a combination of the things on the left. And the thing, the rainbow on the left that you have to add to kill off this new column are exactly the edges that form the fundamental circuit of that corresponding edge in the graph. The observation is that collectively these fundamental circuits determine the sparsity structure of this matrix. And not every spanning tree is made equal. Two different spanning trees, actually the one on the left will have much smaller fundamental circuits because the circuit will kind of just into that center circle and come out. So on the right, you get these huge, long circuits that go around the circle and come back. And once you have this understanding, you can use your geometric understanding about the spaces that you're working with to select out bases that will give much sparser matrices. And since sparsity fill is kind of the main problem in computation, both as far as speed and memory are concerned, that's where you get a lot of speed up. So this is a very low-level kind of a primitive observation that turns out to be a pretty effective one in practice. There's a huge amount that is left to be done in this direction. This connects with all sorts of spectral theory, with Morse theory, with Morse theory. There's a lot going on here, even though you can get out of it with just basic technology.
Thanks.
Mm-hmm.
Any I help in thank Greg one more time. So thank you.
Thanks, everybody.
All right, thanks a lot, Greg.
Thanks.